In this video, we're going to start discussing functions of several variables. So to get started, we're actually going to start with a function of two variables, which we will define. So a function of two variables is a function and it's a function which is going to assign to each ordered pair x, y in some set that I'll call D, which will obviously stand for the domain, a unique number which we'll call f of xy. So this is exactly the same definition of function that you've seen since algebra, except the input now is a pair of numbers, which we're going to call xy, and the output is f of xy. So this is really the only difference here. D, the set D that we just referred to, is going to be called the domain of the function. It's the set of ordered pairs that can be input into the function. And the set of all possible f of xy will be the range. So again, same definitions as in your previous experience with functions. So for a really simple example of a function of two variables that you've seen before, you could talk about the volume of a cylinder. So in this case, we could write volume V as a function of two variables, r and h, standing for the radius and the height of the cylinder. And the volume of the cylinder is pi r squared h. So in this case, our domain would be the set of r and h being greater than 0. Because these are the radius and the height of a cylinder in this context. That only makes sense when it is positive. And the range would also be when we all positive values, because the volume of a cylinder would be positive, and we can get any possible volume as a volume of any possible positive number as the volume of a cylinder. Now I bring this example up, this volume of a cylinder, because you've probably seen it before in calculus, either in related rates or in applied optimization or something like this in Calc 1. And when you dealt with it in Calc 1 and had to deal with it in terms of derivatives, the first thing you had to do was make it a function of one variable. And you usually used some kind of geometric argument to do this, to get rid of the h or the r, depending on what you knew and what you wanted. But in this course, we're going to be able to deal with this function directly as a function of two variables. So some of what we're going to do will help us go back and answer Calc 1 problems in a much more efficient way. Let's take a look at this example. So let's define a function f of xy by the square root of x plus y plus 1 divided by x minus 1. So in the past, when we had a new function, one of the first things you were taught to do is to consider the domain of that function. And that is, figure out what numbers we could input in for x and for x for that particular function. And here we're going to start by doing the same thing, and we're just going to look and try to find the domain of this function to figure out which values of x and y I'm allowed to substitute in. So when I look at this, I see two possible issues with the domain. I see that we have a square root in the numerator, And so whenever we have a square root involved, I know that the thing that we're taking the square root of needs to be greater than or equal to 0. So I do need x plus y plus 1 greater than or equal to 0. And that will make the numerator a defined number. And then the denominator is always defined. X minus 1 has no problems by itself. But because it's in the denominator, we cannot have a 0. And so I also need x minus 1 to not equal 0. Right? And so we can check here. We can do a little bit with these. The first inequality we could write in maybe a more common way of putting y by itself. So y is going to be greater than or equal to negative x minus 1. And we want x to not equal 1. Right, so in terms of writing down what the domain would be, this is about as good as we can do. But one thing we can do here, since the domain is a set of ordered pairs, is we can sometimes sketch a graph of the domain. Right? So in this case, I want to graph this inequality, y is greater than or equal to negative x minus 1. And that's pretty easy to do. We're going to start with our standard coordinate plane. We're going to look at the line y equals negative x minus 1. So that's going to be the line with a y-intercept of negative 1. Right, so it's going to intersect the y-axis down here. It's going to have a slope of negative 1, which means it's also going to go through the point negative 1, 0. Okay. And so our line here looks something like this. Okay. And we want the values where y is greater than or equal to negative x minus 1. So we want the points on that line and everything in between. I'm sorry, and everything above that line. Now, that's just the inequality. Remember over here we want x to not equal negative, or x to not equal 1, and I'm sorry, that should be an x not equal to 1. Not x equal to 1. But we want x to not equal 1. So on this graph here at x equals 1, we're going to have to take this little line, and I'm going to draw this in blue, and we're going to have to just remove that x equals 1 line from this graph. All right, so the best I can do is make that a different color. So the domain here in the picture is everything that's shaded in red except for that blue ray that starts on the line at the point 1, negative 2, and goes upward forever. Right, so this is the entire domain. Now once we have a point in the domain, to evaluate the function at the point is just as easy as it is with standard functions. So for example, if I wanted to know what the value of f of 3, 2 would be, right, what we would do is just substitute 3 in for x and 2 in for y into our function. So this will be 3 plus 2 plus 1 all over 3 minus 1, and this would be the square root of 6 divided by 2. Right? And any other function evaluation is just as easy. We just substitute the first number in for x, the second in for y, and simplify to whatever degree we need to. Let's take a look at another example. So let's say we wanted to find both the domain and the range of the function f of xy equals the square root of 9 minus x squared minus y squared. Right? Now in the previous example we didn't find the range, and that's because there was really no nice way to do that. In this particular one, because of the form of the function, the range ends up being a really nice region that we can describe. So the domain, this looks a lot like what we did in the previous one. The issue here with the domain is that we have a square root, so we do need the quantity under the square root to be positive. So we need 9 minus x squared minus y squared to be greater than or equal to 0. So it can equal 0. So we want it to actually be non-negative, not positive. And so if we just rearrange this a little bit, we can see that this is the same thing as x squared plus y squared less than or equal to 9. And so this is the equation of a disk centered at the origin with radius 3. Right. Now I use the word disk here instead of circle. A disk, when we're talking about a disk, we're talking about the circle and the interior. Right? Geometrically, when we talk about the circle, we're just talking about the points on the circle. That would be x squared plus y squared equals 9. But we want x squared plus y squared less than or equal to 9. So the less than 9 will give us the interior of that circle. Right? So this function is defined everywhere on the inside or on the circle centered at the origin of radius 3. And so it's only defined on that particular region of the xy plane. Now our range here, like I said, we can actually describe the range pretty nicely. What we want is we want all values of z. We'll introduce a third variable. We want all values of z where z is equal to the square root of 9 minus x squared minus y squared. So if we analyze this, we can see that z has to always be greater than or equal to 0 because it is the square root of some number, so it can never be negative. And also that the largest z could possibly be is 3. Right? If x and y are both 0, we get z equals the square root of 9, which is 3. But if x or y, if either of them are not 0, then we're actually going to subtract something from 9 and then take the square root. And so this number will be less than 3, or would be less than 3. So z has to be somewhere between 0 and 3. Now, if I then take this equation and the original equation that I had for the range, z equals the square root, and I square both sides, we see that z squared is going to equal 9 minus x squared minus y squared. And we could rearrange this to have x squared plus y squared plus z squared equals 9. So our range in this particular example is the set of values z between 0 and 3, including those endpoints, which satisfy the equation x squared plus y squared plus z squared equals 9. Right? And we're going to come back to this example in just a moment. Now that we know how to find the domain and range of a function of two variables, one of the next things we could try to do is graph these functions. And so we have to start by making sense of what it means to graph a function with more than one variable. And so for two variables, this is pretty easily done. So we're going to define the graph of a function z equals f of xy, so a function of two variables, with domain D which is some subset of R2 of the plane. So the graph is going to be the set of ordered triples XYZ, where xy is a point in the domain of the function, and z is actually equal to f of xy, whatever real number that function outputs. Okay. And so the graph works exactly like we did in algebra and in calculus before with functions of one variable. The only difference is now these graphs are actually going to be surfaces in three-dimensional space as opposed to curves in the plane. So let's look at the example that we just talked about. That was z equals the square root of 9 minus x squared minus y squared. And in that example, we saw that we wanted z to lie between 0 and 3, and also to satisfy the equation x squared plus y squared plus z squared equals 9. And so if we just look at the equation here, this we should readily recognize as a sphere centered at the origin with radius 3. And so you might think initially that this graph is going to be a sphere. But we do have to pay attention to this inequality 0 to 3. This is on the z-axis, so we only want the part of this sphere that lies above z equals 0, which is the xy plane, and below z equals 3, which is that plane 3 units above the xy plane. Well, if the sphere has radius 3, the very top of the sphere will intersect the plane z equal to 3. And the xy plane will actually cut right through the middle. So this inequality tells us that we don't want the entire sphere. We only are going to have the top half of the sphere for this particular graph. Right, so that graph will look something like this. We have the domain. You can see underneath this particular graph would be the circle x squared plus y squared equals 9 in the xy plane. That's what our domain was we found in our previous example. And for each point in that domain, we have a point that lies, in this case, above the xy plane. It could be on or below as well, but in this case it's above, or at least on the edge of the circle, it is on the xy plane. But we get a value of z for each ordered pair xy in that disk, and that z gives us our height of our graph. So we can do one other quick example where we can figure out the graph by hand. So let's say we had the function f of xy, and it's equal to 6 minus 3x minus 2y. Okay. Well, if we want to try to figure out what this is, the only way we can do this by hand in a clean way is to input a z in for f of xy, and rearrange the equation so that it looks like something that we've seen in the past. And so if we move the x and y terms on the same side as z, we get the equation 3x plus 2y plus z equals 6. Right? And this is a type of equation that we've seen before. And this we should readily recognize as a plane. And in order to describe this plane, the only thing we can do right here is we can describe it with its normal vector, which would be 3, 2, 1. Right, so this is a plane. We know its normal vector, and so we can go about, if we needed to sketch this, we could. But at least in this case, we know what the graph is going to be. It is going to be a plane, and we can use the normal vector to figure out sort of what the graph would look like. Right? So we've seen these two examples where we've been able to rearrange algebraically the equation for the range, for the function, and we've been able to recognize the two forms of the equations. Of course, that's not always going to work. So for example, if I had this function, if I had f of xy equals 9x squared plus 4y squared. Right? Even if I replace the f of xy with z and I rearrange this in however different ways I wanted, I would never recognize what this shape is, what this graph would be, because we haven't looked at this particular type of graph before. And so if we wanted to figure out a graph of this, we really don't have a choice unless we want to just plot some points in three-dimensional space and try to figure it out that way. But usually the best thing to do is to use technology to get an idea of what this would look like. And so it's going to look something like this. Right? Now this makes sense. I mean, if you look at the form of this, 9x squared plus 4y squared, you can see that z is never going to be negative because we're adding together two positive numbers. You can see the only time the z value is going to be 0 is when x and y are both 0, which is why the graph sort of comes to a point down at the origin. And as we increase x and y, as we go out further along the axes, you can see that the z value gets larger and larger. So despite the fact that we use the technology here, there is one way that we can sort of by hand help analyze the shape of this particular surface, and that will become important a couple times when we go through the rest of this course. So we're going to take a look at that particular concept now. Okay, so if we're given a function of two variables, we're going to define the level curves of this function as the curves f of xy equals k, where k is some constant. And the way that we're usually going to deal with this is by letting k be several different constants and plotting each of the curves together in a single plane. Now, one thing to point out before we look at any kind of example of this is that when I refer to this as a curve, this is an equation where we have an x, a y, and a constant. And so this curve is actually a curve in the plane. This is not a three-dimensional curve, right? This is a two-dimensional curve. There's no z here. So we're going to take a look at the graph of the function we just looked at on the previous slide, z equals 9x squared plus 4y squared. This is the same graph that we just looked at. And in the graph, this includes 9 little what look like maybe ellipses that are going around the outside of this graph. So these are actually cross sections of the shape by taking planes z equals a constant k and intersecting them with with this surface, with this graph. And so if I take k equal to 1, the level curve with k equal to 1, set the graph equal to 1, the image is this circle right here. So this is what happens when k is 1. That's the level, that's the intersection of z equal 1 with this surface. When I take k to be 2, we get the second circle. That's the intersection of z equals 2 with the surface. And if I take the k equal to 9, I get the one on the very top. All right, that's the intersection of our surface with the plane z equal to 9. And of course, k equal to 3, 4, 5, 6, 7, and 8 are all depicted here as well. Just to keep the labeling simple, I won't label all of them. So then these level curves, when we take this intersection of the plane, when we let z be a constant k, we can graph all of these in a particular in the xy plane. And when we do this, we get this particular picture. Right? And so you can see that what we have is these ellipses given by 9x squared plus 4y squared equals k. And k is going to range from k equal to 1, which is the innermost ellipse. The next one out would be k equal to 2. And to sort of, again, save some space, this would be k equal to 9. So not to draw all of them. But the idea here is that if we take those plane curves, f of xy equals 1, we will sketch this curve, this innermost ellipse, on the right side graph. And so what we can do is we can use these level curves to analyze what the shape of this object would be. So from just the picture on the right, we can conclude that the surface in three-dimensional space must have a cross-section of an ellipse at every value, because all of these different cross-sections are ellipses. We also know that we've increased z by 1 from each ellipse to the next ellipse. So the innermost one is when z is 1, the next one is z equals 2, the next one is when z equals 3, and the outermost is when z equals 9. And so if you look carefully at this, you see that these ellipses, as z gets bigger, are actually getting closer together, which actually would tell us that this graph, as we get further and farther up on the z-axis, this graph is getting closer and closer to a vertical graph. Of course, it'll never become vertical because then we would not have a function. But we know that this graph is sort of leveling out to be as close to getting closer and closer to being vertical as we get higher up. So it's not going to be as a steep of change as we go up. And so, in various contexts, you might use level curves to study what this graph would look like if you didn't have technology available to give the entire graph.